waves, we're going to be looking at one more wave phenomenon that we didn't look at in 6.2, standing waves, fundamental harmonics, and resonance. We didn't look at this in 6.2 because this topic is so important that it deserves its own separate lesson. Okay, so that's the topic for 6.3, fundamental harmonics and standing waves. So first we need to take a look at what is resonance and what are standing waves. So, as we've already talked about in 6.2, if two waves are in phase, constructive interference will occur, resulting in an amplification of amplitudes of resulting waves. Okay? If this is occurring with total in-phase constructive interference, okay? Otherwise, we'll have beats like we saw, but if we have total constructive interference, the amplitudes will continue to increase and amplify, and this is a phenomenon that we call resonance, okay? So under such circumstances, the waves have matching frequencies or frequencies that are whole number multiples of each other, a condition that we'll take a look at in more detail in a second. So thus the waves are going to completely overlap and cause constructive interference, okay? So as an example of resonance, the classic case is an opera singer shattering a wine glass, okay? The frequency of the sound waves matches the frequency of the molecules that make up the wine glass, which causes the molecules to vibrate uncontrollably, causes them to amplify uncontrollably until the point that it breaks down the structure of the wine glass and the wine glass breaks. We're looking at this as just a basic level right now, so if you want to know about this at a more detailed level, that's where you'd have to look into material science, and you'd also have to look at damped oscillations and resonance harmonics, which is a topic that's looked at in higher level mathematics and physics courses with where calculus is involved. Okay, so right now we're just getting just a very superficial look at resonance and examples of resonance, such as the opera singer shattering a wine glass. Okay. The wine glass, in fact, everything from swings to harmonic oscillators and molecules has a set frequency due to its internal structure, aka the molecules that make up our wine glass like we talked about, and this is what we call the natural or fundamental frequency of our object, whether it's a wine glass or swing or harmonic oscillator or a molecule, okay? So for example, like a swing, you've noticed if you push with a certain frequency on a swing, the swing will get higher and higher and higher, whereas if you don't push at that frequency, the motion of the swing can die out and fizzle out. So when the opera singer sings at a frequency that matches or is a multiple of the fundamental frequency, the sound interacts with the glass to cause an amplification in the amplitude of the molecules that make up the glass until the internal structure fails, causing the glass to shatter. So let's take a look at what fundamental harmonics are within the context of strings and what causes resonance in waves with strings, okay? So standing waves. Standing waves are waves that oscillate vertically, but horizontally do not move, okay? Meaning that you don't notice any wave motion from left to right, like we've seen so far throughout this unit, okay? So the wave just seems to oscillate up and down, like when you pluck a guitar string like this right here. So as a result, we say it's a standing wave because it seems to stand in one place, in one single place, and oscillate vertically up and down. The amplitude of the wave stays at one horizontal point instead of propagating along the string. So this amplitude is never going to move from left to right. This amplitude is always going to stay right at the middle and oscillate up and down. So again, examples like a plucked guitar string. The point plucked, the amplitude oscillates vertically but does not move from left to right. So a standing wave is formed due to a combination of reflection and interference for a continuous wave source. That sounds like a whole bunch of garble, so what do I mean by that? Let's take a look. Okay, so again, a standing wave is formed due to a combination of reflection and interference for a continuous wave source. So what we're going to take a look at right here is an example right here where we see this happening. So what we have is this wave that's in a tube right here, okay? What we can see is that the wave, when it reaches a boundary, is going to reflect off, which is the orange wave right here, okay? And then we're going to have continual reflections like we see happening right here. So the orange wave will reach one end and then reflect off as a blue dotted wave, and then the blue dotted wave will reflect off. And you're going to have all these multiple reflections going, okay? So what's going to happen here is that if you have the right conditions for the length of this tube and for the wavelength of the waves inside the tube, what's going to happen here we can see the amplitude is greatly increasing now, or has greatly increased. And what's going to happen here is when the wavelength and the air column length, or the length of our column here, meets certain conditions, what's going to happen is that at certain points, all of our waves and wave reflections are going to result in constructive and destructive interference. So if we look at this point right here, this point goes through destructive interference and then constructive interference when the reflection and wave overlaps, okay? So right here we can see total reflection total constructive interference. We'll wait for it to come back one more time. So right here we can see total constructive interference when the wave and its reflection overlap, and then total destructive interference right here when they're out of phase with each other, okay? So as a result, it looks like the amplitude oscillates vertically up and down, but it does not look like the amplitude is moving from left to right. Likewise, right here, at this point right here, we notice that this point does not oscillate up and down because this point is going to be going through continual out of phase, complete destructive interference. So this point is never going to oscillate. It will seem frozen and remain in place like it's standing in one place. Hence why we call it a standing wave. So the points where amplitudes occur due to constructive interference is what we call antinodes. Okay. So right here would be an example of an antinode. Okay. And while the points that are fixed and do not oscillate due to continual destructive interference are called nodes. So these points right here that we see that stay at one point and do not oscillate up and down are called antinodes. And then these points right here that oscillate up and down, going from that one amplitude to the other end of the amplitude, is what we call an antinode. Okay, so the point where we have the standing wave reach its amplitude at is what we call antinodes. Okay? And then here's a nice little visual for you. The nodes, again, are those parts that undergo continual destructive interference, and the antinodes are the parts that go from amplitude to amplitude. Okay? So what are the conditions then for fundamental harmonics to form and standing waves to form? So we can have different types of instruments that our waves are in. All right. So the first type of instruments that we can have, or first type of scenario we can have, is what we call closed scenarios, okay? So if the boundaries of a wave are both closed or fixed, the wave will have nodes at the boundaries. This is like a guitar string, okay? A guitar string has a fixed or closed end because these strings are fixed at the ends. So as a result, those are going to be nodes at the ends or at the boundaries because they're not free to oscillate up and down. So in this case right here, when we have closed like this, what we can take note of is that we have 1/2 wavelength fitting in here. Right here we have 1 full wavelength fitting in here. And then right here we have 1.5 wavelengths fitting in. Okay? So the length L of the tube will always be a multiple n of 1/2 of the wavelength. Notice here how we have 1/2, and then we have 2 halves, which gives us just 1 whole wavelength. And then right here we have 3 halves, which gives us 1.5 wavelengths right here. Okay? So length L of a tube will always be a multiple n of 1/2 of the wavelength. So for closed, the harmonic number is the number of antinodes of the wave right here. Okay? So for closed, number of antinodes. So right here we see we have 1 antinode, so our harmonic number is n equals 1. Okay? Right here we can see that our harmonic number is n equals 2 because we have 2 antinodes, and right here we can see we have a harmonic number of 3 because we have 3 antinodes, okay? So the wavelength for an nth harmonic in a closed system is going to be 2L divided by n, where n is a harmonic number. So this is the wavelength for the nth harmonic standing wave, okay? How we get this equation, again, is taking notes, is that the length of the L of the tube will always be multiple n of 1/2 of the wavelength. So right here, our length of the tube is 1/2 of the wavelength. Right here, our length of the tube is 1 full wavelength, and right here, length of our tube is 3 halves of the wavelength. So we have L equals n divided by 2 times the wavelength, where n, again, is our harmonic number, the number of antinodes we have. And solving this equation right here gives us 2L divided by n for our wavelength of the nth harmonic. Okay? So this is for closed. So the same result is going to apply for an open scenario, okay, as 1/2 multiples of the wave fit into the tube, okay? We see right here that we have 1/2 wavelength fitting into a tube, so our tube length is 1/2 of a wavelength. Right here we can see we have one full wavelength fitting our tube, so our tube length is one full wavelength, and right here we can see we can have 1.5 wavelengths fitting in here, aka 3/2 wavelengths, so the length of this tube is 3/2 wavelengths, okay? The only difference now is that harmonic number of an open tube is going to be the number of nodes of the wave, okay? So whereas with closed, we count the antinodes, with open, we count the nodes to get the harmonic number. So right here we're going to have a first harmonic because we have one node. In this case, we're going to have a second harmonic because we have two nodes, and then right here we're going to have a third harmonic because we have 3 nodes. Okay? So as a result, we have the same condition as before, where our length of our tube is going to be a 1/2 multiple of the wavelength for our standing wave, and thus the wavelength for the nth harmonic standing wave is going to be 2L divided by N. This equation is not on your equation sheet, and it must be known. Okay? And then lastly, we come to a closed open case, okay, where one end of our boundary is closed, to say it's like it's fixed to a guitar string, and then the other end is open and free to move up and down, okay? So in this case right here, what's going to happen is that since this end is free to move up and down, we're going to have an antinode right here, and this end is fixed, we're going to have a node right here. So we have 1/4 of a wavelength that fits in right here, okay? Right here we can see we have 3/4 of a wavelength that fits in right here. And then right here we can see we have one full wavelength and a half wavelength, or in terms of a fraction, 5/4 of a wavelength, okay? So, as a result, the length L will always be a 1/4 odd multiple K of the wavelength, okay? Why do we say 1/4 odd multiple K of the wavelength, okay? So the reason being right here is we're always going to have an odd number of antinodes here, okay? So in this case right here, K would be 1. In this case right here, or excuse me, not odd number of antinodes, but we're always going to have an odd number of wavelengths fitting in here. So we have 1/4, all right, so N equals 1/4 of a wavelength fitting in here. N equals 3/4 of a wavelength fitting in here, and N equals 5/4 of a wavelength in here. So our harmonic number is always going to be odd, okay? So how do we get K then? So actually this should actually say N right here instead of K. So N and K are going to be slightly different. K are going to be the number of antinodes counted, okay? So in this case right here, we're going to have one antinode, and then in the second case we're going to have two antinodes, 1 and 2. And in the third case we're going to have 1, 2, 3 antinodes. So if K is the number of antinodes that we count, how do we get N to be equal to 1, N to be equal to 3, and N to be equal to 5 for our harmonic numbers, okay? So what we do is we take the number of antinodes counted, which is K, and we use the following relation to get our nth harmonic, okay? So N is going to be equal to 2K minus 1, okay? We can only have an odd number harmonic because, again, we can only fit in an odd multiple of 1/4 wavelengths into the tube. So again, this should say N, not K right here. So we can only fit a 1/4 odd multiple of the wavelength into a tube. So thus, our harmonic must always be odd. So how do we get the harmonic? Well, we take the number of antinodes we count, we multiply it by 2, we subtract by 1, which is the formula that you get for an odd number in math. Any number multiplied by 2 will give you an even number, and if you subtract that by 1, that always gives you an odd number, okay? So the process here to get your nth harmonic for an open-closed system is to count the number of antinodes K you have, and then turn that into an odd number by multiplying K by 2 and subtracting 1, and that will give you your nth harmonic, okay? So only odd number harmonics can occur for the open-closed scenario like we talked about because we can only fit 1/4 multiples in here, 1/4 odd multiples in here, so 1/4, 3/4, and 5/4. So as a result, your length L of your tube is going to be your harmonic number divided by 4 times your wavelength, where N again is an odd number, all right? And then your wavelength, as a result of solving for the nth harmonic, is going to be 4L divided by N, okay? So this equation right here, 4L divided by N equals your wavelength, must be known. And again, please take note, we can only have odd number harmonics for open-closed systems or closed-open systems, okay? So here's a problem-solving schema then for dealing with harmonics, okay? If we are given a wave diagram, okay, like we've had at times throughout this unit, what you're going to do is you're going to count the antinodes to get the harmonic, you're going to calculate the wavelength or length of your tube, and then you're going to calculate the fundamental frequency from the harmonic number, okay? And then what you're going to do, once you've done these three things, okay, is that you're going to use a wave speed equation to determine your unknown quantity, okay? So oftentimes what they'll do is they'll give you a wave diagram and they'll ask you to calculate the harmonic, to calculate the harmonic number, or excuse me, they'll give you a wave diagram, they'll ask you to calculate the wave speed, which requires you to know wavelength and frequency, okay? So what you'll do is you'll count the antinodes, which you can then use to calculate your wavelength or the length of your tube, and also calculate your frequency from the harmonic number. And that will allow you to use the wave speed equation to determine your wave speed, your unknown quantity, okay? Now, let's say now instead of being given a wave diagram, we're given wave speed, frequency, or wavelength. So here in this case, we're going to start with the wave speed equation to solve for our unknown quantity, whether that unknown quantity is wave speed, frequency, or wavelength. And then we're going to move our way to using the harmonic number to calculate our length of the tube, or to calculate the antinodes, or to calculate the harmonic number, or to calculate the fundamental frequency, okay? So this problem-solving process, as with every problem-solving process that we see in physics, can seem quite esoteric, abstract, and difficult to work with. But again, we're going to expose to example problem here, and then in class we'll get more and more practice with it so it becomes part of our problem-solving repertoire. So example 1, harmonics from a diagram. A harmonic oscillator is used to create a standing wave and a 6-meter long string with a fixed end and an open end, as shown right here, okay? A asks, what is the harmonic number of the wave, okay? So in this case, we have to think about, are we dealing with an open-closed, closed-closed, or open-open scenario? Here we're dealing with a closed-open scenario, so we're going to count the harmonic number by first counting the number of antinodes we have. In this case, we have 1, 2, 3 antinodes, okay? So as a result, we're going to use the equation for the harmonic number of a open-closed scenario, which is going to be 2 times 3, our number of antinodes, minus 1, which gives us that our harmonic number, n, is 5. Remember that we always have to have an odd number here, so we use 2 times the number of antinodes minus 1 to get our harmonic number. B asks now, what is the wavelength of the wave? Okay? So what we can do right here, okay, is we can count the number of waves that we have here, and we can compare that with the length of the tube, okay? So in this case right here, we are looking at a fifth harmonic, okay? So we can use the wavelength equation for an open-closed scenario where n is equal to 5 for the fifth harmonic, okay? So our wavelength here, using the wavelength equation that we solved for open-closed scenario, is going to be 4 times L divided by our harmonic, which is 5. If our wavelength right here is if the length of our string is 6 meters, that means we're going to have 4 times 6 divided by 5, which means that the wavelength of our fifth harmonic standing wave is going to be 4.8 meters, okay? So lastly, we move to C, where C asks now, if the frequency of the oscillator is 60 hertz, what is the fundamental frequency and wave speed? Okay? So here we can figure out the fundamental frequency by taking note of the fact that our fundamental frequency is related to the fifth harmonic by 5 times F1 equals F5. Okay? Again, our harmonic frequency, our nth harmonic frequency is always going to be the nth multiple of our fundamental frequency. So if we're looking for the fifth harmonic frequency, that's going to be 5 times our fundamental frequency. Okay? So here, we know this is for the fifth harmonic, so we know our fifth harmonic frequency is 60 hertz. All right. So as a result, we're going to have 5 times F1 equals 60 hertz, which if we divide both sides by 5 will give us F1, our fundamental frequency, which is 12 hertz. Okay. So now our wave speed can be found via the wave speed equation. Okay. Here, even though we found fundamental frequency in this first part right here, the fundamental frequency refers to the fundamental frequency for the material. It does not refer to the current frequency of the material at the fifth harmonic. In this case, our current frequency is 60 hertz. Okay, So as a result, for our wave speed equation, we're going to use the fifth harmonic frequency and the fifth harmonic wavelength, okay? So the fifth harmonic wavelength is 4.8 meters, and the fifth harmonic frequency is 60 hertz, which tells us that the wave speed is 288 meters per second, which means you probably don't want to stick your hand in this wave right here because it will probably, it's not going to be too pretty, all right? Anyway, so this is an example of the problem-solving schema we can use with harmonics, okay? Again, it can seem a little bit daunting at times, as with all problem-solving processes in physics, but the more practice we get with it, you'll see the more adept you'll become at solving these types of problems.